So we showed how Moore's Law is pushing forward our PXI platform. Now we want to show how Moore's Law is fundamentally changing the game for one of the most challenging applications that you face, and that's the design and test of wireless systems. Now, Charles, I joked about you being a marketing guy earlier, but in truth, you've spent almost your entire career in R&D, and you just recently moved to marketing. Why don't you tell everyone why?
Well, thanks, Eric. So several years ago, I got an amazing opportunity to join a very, very special R&D team with the goal of starting with a blank sheet of paper and completely redefining from the ground up how instruments are designed and how instruments are used today. And as one of the chief architects on that team, I was really so excited about what we were building that I moved to marketing a year ago just to help the marketing organization plan the release of this product. You know, you've mentioned already, Eric, that in the PC industry, Moore's Law has of course given us faster performance, but it's done so also giving us smaller size, lower power, and lower cost. It's helped us to integrate multiple functions into a single device. And most importantly of all, it's allowed us as users to customize the way we use our devices through software. And unfortunately, as you also mentioned, the test and measurement industry has not kept up. You know, they've used Moore's Law, but only to increase the performance of the products. But as we began to redefine and rethink how instrumentation was designed, it was very important for us to, of course, improve performance, but to do so also using all of the benefits that Moore's Law has to offer. So today, at NI Week, I'm happy to start to show the fruits of our labor. We've taken 4 traditional RF instruments, an RF analyzer, an RF generator, digital I/O, and an FPGA, and put them all into an ultra-small, very compact form factor, a single 3-slot PXI chassis. And we've done so while making the cost down to just the price of one of the instruments by itself. In fact, the hardware design is so elegant, you get all that functionality and less power than a single 60-watt light bulb. And today, for the world's first time, I'm happy to show you the introduction of the first vector signal transceiver. Now, Eric, that's marketing.
All I can say is, oh, wow.
All right, but enough of the fluff. I really want to get to the demos and show you all the amazing uses for this new product.
In order to show off the RF performance of the new NI vector signal transceiver, we're going to compare it to a high-end RF box instrument from Agilent. The test case we'll use is an error vector magnitude, or EVM measurement, of a pre-release Wi-Fi standard called 802.11ac. Now, 802.11ac is a challenge to test because it requires the instruments to have a low phase noise, wide bandwidth, high linearity, and a low noise floor at frequencies greater than 5 gigahertz. So in order to provide a reference of how good the RF performance of the new NI vector signal transceiver really is, we're going to compare it to the industry's gold standard, the Agilent PXA. As you can see on this LabVIEW VI, we're generating and measuring a 256 QAM 802.11ac signal, and we're comparing the EVM floor of these two instruments. As you can see, the Agilent PXA measures an EVM of about -44 dB and around 400 milliseconds. By comparison, the NI vector signal transceiver measures about -49 dB at around 22 milliseconds. Now keep in mind that this difference of more than 3 dB means that the vector signal transceiver has less than half the inherent error of the Agilent PXA. So not only does the new NI vector signal transceiver offer better performance, and it's substantially smaller than the PXA, but it's got almost 20x measurement speed as well.
Wow. Now, I know you guys have plenty more to show, but I want to pause there for a second because what you've already shown is very significant. That little small 3-slot module over there just outperformed the gold standard RF box instrument, and it did so at a fraction of the size, power consumption, and cost. And it also was testing a wireless standard that isn't even released yet. It's really impressive. And now, Charles, you mentioned that the FPGA is part of this product, so why don't we talk about the role the FPGA plays on the vector signal transceiver?
Yeah, we're getting to the most exciting part. You, our users, have been wildly successful in the last couple of years using LabVIEW and LabVIEW FPGA technology to build amazing world-class test systems. But with the vector signal transceiver, we wanted to take things one step further. And so with this product, we're introducing a brand new concept and a brand new paradigm and shift in instrumentation that we're calling software-defined instrumentation. You see, with a vector signal transceiver, We've provided all of the software on the host and the driver, all the way in the firmware of the instrument. Everything is provided to you as open source LabVIEW and LabVIEW FPGA code. So with the vector signal transceiver, not only can you use the product with an out-of-the-box standard instrument driver API, but you can drill down into that software layer by layer, all the way down into the firmware of the instrument, touch the pins of that instrument, so that you can make specific customizations to improve the performance or the functionality of the instrument for your application. We call this software-designed instrumentation. And I think as you're about to see in the next demo, with an incremental change to the LabVIEW software in the product, we can make revolutionary gains in performance.
The example I'm going to show is a power level servoing test for RF power amplifiers. Now, servoing is an iterative process where we generate a stimulus, measure the response, calculate an error, and then adjust the stimulus until we reach a desired power output level. Now, with traditional instrumentation, this is a time-consuming process, as much as 5 seconds per measurement. And most of this time is actually spent controlling the instruments themselves. But with the NI vector signal transceiver, we can remove much of this instrument downtime by moving the loop logic from the host down to the FPGA, much closer to the device under test. So let's see this in action on a power versus time graph.
Okay, let's see. We got the graph up there, Eric. I see the black curve, which is the traditional boxes here, ramping up to the correct power. It takes several seconds, but I don't see the vector signal transceiver on that.
Well, that's because the test time reduction is so great that I have to zoom in multiple times on this graph just to see it. So as we can see here, the loop logic that took almost 5 seconds on the host, when that same logic is moved to the FPGA, takes less than 5 milliseconds. And that is a test time reduction of 3 orders of magnitude, which is over 800x in a test time reduction. Wow.
And I just want to iterate what you've seen today, because it's pretty amazing. What Eric did was he took a LabVIEW VI with a control algorithm written on the host, and he moved that VI, simply put it down into the instrument firmware itself, and by that simple change was able to achieve over 800 times the performance of the measurement speed. It's pretty amazing.
It's also shows the benefit of having a common platform that serves these different domains. Here we effectively took IP from closed-loop control systems and put it in this RF measurement system for such a dramatic performance improvement. Now, Charles, since the firmware of the device is completely defined in Open LabVIEW software, it can also address applications completely outside of traditional test and measurement. Let's share one of those.
That's right. And for that, I'd like to introduce Dr. Ian Wong to show us a different type of application. Now, Ian, you've been in R&D for several years working on the design of next-generation wireless standards. Can you tell us how you're using the vector signal transceiver?
Sure, Charles. The new vector signal transceiver in many ways is like the combination of a high-end RF instrument built on the architecture of a software-defined radio. It makes it an ideal platform for wireless engineers like myself to design, prototype, and deploy the wireless systems of the future. So one of the toughest challenges for a wireless engineer is to understand and characterize and find ways to combat the harsh wireless propagation environment. Say, for example, as RF signals travel over the air from a base station to your handset, it suffers from a lot of impairments like Doppler spread caused by mobility, reflections off of buildings and walls cause a lot of frequency selective fading, and also interference from neighboring base stations cause a lot of intercell interference. As you can imagine, this is very challenging for a wireless engineer, and it's very important to be able to bring that environment back into the lab in a controlled and repeatable manner. And the way we can do that is by using an instrument called a radio channel emulator.
All right, so Ian, I think what you said is in a radio or a real-time channel emulator, what the function of that device is to take the pure signal that comes out of your cell phone and the pure signal that is measured by an instrument, and to emulate the air and the real-time environments in the lab so that an engineer can be sure that when they release their new mobile phone device, that it will work under any operating condition.
That is absolutely right, Charles. And as you can imagine, to build a channel emulator, it's very taxing on the hardware requirements. First of all, we need very pristine RF inputs and outputs. We need a tightly coupled large FPGA to model all of these impairments in real time. And to, excuse me, and in order to do MIMO, we even need sample and phase synchronization and large streaming across the FPGAs on the device. It just so happens that the vector signal transceiver has all of that from a hardware perspective. But more importantly, because of the software design instrumentation paradigm, it allowed me to rip out the entire firmware and implement this completely new instrument out of the vector signal transceiver. So let's see it in action. So on this front panel right here, you're seeing two vector signal generators that are generating the MIMO signals through our two vector signal transceivers acting as our MIMO channel emulator and being analyzed by two vector signal analyzers. And we're plotting the spectrum right here, which is kind of like the signal on your cell phone that you're seeing, that you're holding in your hand. So right now what it's doing is it's just kind of pushing this signal across pristine signals. It's acting like a fairly expensive cable. But what's interesting about this is now I can actually add, for example, a reflector at about 100 nanoseconds and see its effect on the received spectrum, which is showing these spectral nulls on the first antenna. May put another farther away reflector and see even more nulls, and it's extremely important for a wireless engineer to see this and design their device as well. But more interesting is to be able to do a standard specific, more realistic channel model, like in this case, someone walking down the street, or of course, driving down the highway. And we can even increase the velocity right here, as you all know Texas drivers love to do.
All right, so while the 2x2 MIMO demo that you've just seen is one example of how engineers can use the new vector signal transceiver as a real-time channel emulator, there's a wide range of applications in the embedded and research space that would also benefit from having an RF input, an RF output, and an FPGA tied together in a loop. Other examples include software-defined radio research, base station emulators, digital predistortion, and many others.
Well, thanks, Ian. I think you've really started to give people a glimpse of how a software design instrument can really allow you to think completely differently about how you design and test a communication system. And thanks, guys.